Alright, how's everyone doing today? My name is Brison Louque, and I'm the leader for Group 3, and this is the rolling experiment. We're actually going to be doing experiment 1, so I misread the schedule. I ended up doing experiment 3. Cops being real cool about it, kind of let me slide a little bit. Still got to do experiment 1 next week. Anyways, so I did the air conditioning charging experiment. So basically, the main goal is to calculate the coefficient of performance and how it is affected based on the charging pressure of a refrigeration cycle. And the way coefficient of performance is calculated is, what it actually is the ratio of the magnitude of the desired commodity to be created, or the one that's wanted, over the magnitude of the expenditure. So basically, it is the ratio of the output over what you put into the system. And for the refrigeration cycle, the input are not really the refrigeration cycle, but heat pumps in general. The desired commodity is either cooling or heating, depending on what your application is. And the expenditure is the power consumed in order to achieve that cooling or heating, which is typically through power input into a motor that drives a compressor. So right here, kind of went into what a heat pump is. But a heat pump is basically used to change the temperature to either maintain a lower or higher temperature in a system compared to the ambient temperature that is the input of the input fluid. So that makes heat pumps versatile. You can either use them to heat or cool things. So in cooling, the coefficient of performance is signified as beta, which is the QL over work in, QL being the lower heat transfer which occurs at evaporators, and the work in is the work put into the compressor to drive the fluid. Now, this was deduced in the thermal book where I was reading and getting all my data from, but in hindsight I realized that the TH over TH minus TL actually refers to the air that is passing through the cycle. So my calculations outline, I will correct them as I go. And I'll point out where I made mistakes and where I can improve. But still, we're going to continue with the presentation anyways. So basically, the experimental objectives are to perform a thermodynamic analysis on air conditioning system. And we want to learn the effects of charge level on the performance of an air conditioner. So we want to see whenever we raise or lower the charge pressure in an air conditioning unit, what does that do to the performance of it? Does it make it run more efficiently? Does it make it run less efficiently? And so the way the experiment is set up, you have this simple cycle here. It's your typical refrigeration cycle. It's actually the same exact cycle as a heat pump cycle, if you want to get something warmer, but it's kind of backwards. So what you got is your compressor, which drives the fluid within the tubing, and that flows to your condenser, which actually takes your working fluid. I say working fluid, but it's your freon, your coolant, and it condenses it, obviously. By doing that, it removes the heat from that fluid and releases it into the atmosphere. So that's why you would notice whenever you pass by your refrigerator, the bottom's real hot, because that's where your condenser unit is. And once it gets to your condenser, it goes through capillary tubes, which are used to expand the gas. And through expanding the gas, it makes it more suitable for when it passes through the evaporator to get the proper heat transfer and provide the cooling to the air that it needs to achieve the goal of cooling the air in the room. And between each set, we have pressure and temperature taps, which will let us keep track of what the pressure and temperature is at each stage in the cycle. And by doing that, we can really observe what effects that the charge pressure has on the refrigeration cycle. All right, so like I said earlier, we're going to run the refrigeration unit at various charge levels. And the way it's determined how much charge you have in the system is by weighing the reservoir. As you increase the amount of charge on the system, the weight of the reservoir is going to decrease. And you're going to decrease it until you can no longer get any more Freon out of the reservoir, and by then it should be around 17 to 18 pounds total. And once it's at that weight, it'll probably stop putting out Freon, and then you can stop the experiment. And for each one, you're going to observe the differences in the COP for each charge pressure that you use. Typically, you go in increments of half a pound of weight on the reservoir. So in the previous experiments, the way I interpreted this is that we had these pressures of 500 kilopascals and 1200 kilopascals. 500 coming out of the condenser, that was the pressure of the Freon coming out of the condenser, and 1200 kilopascals was the pressure coming out of the evaporator. So using this, I actually went into I used the data sheet on Freon 22 provided by Dow, which was one rule, and I was able to figure out what temperatures Freon would be at those pressures. Now, this is pretty much how I went through with it, and I plugged it into my coefficient of performance equation that I had, and I was able to get a coefficient of performance of 10.096. So that is really high. That is really wrong. And the reason is because, like I explained earlier, I believe the high temperature over the temperature, high minus temperature low, is actually for the air that's going through the system and not the Freon itself. That's your refrigeration cycle. That's what it looks like on a TS chart. That's what it looks like on a pH chart. And that's my references. So if anybody's got any questions, just feel free to ask.
If you were to use water as your liquid going through, how do you think that would change your coefficient of performance?
You lock the compressor up. Because you can't really compress water. You can, but you can't. It would be good for the compressor, I know that. But if you use water with something else like a pump, I mean, it wouldn't be as efficient because the condensing and evaporation of the gas is what makes the refrigeration cycle so effective, because so much energy is required for between the states of complete vapor and complete saturated vapor and complete saturated liquid.
What if we use nitrogen?
It doesn't have the same cooling properties as Freon, so I believe it would be less efficient, but it would still work to an extent. But actually, if you use nitrogen, then you have the same, you're going to have the same, almost the same properties as the air surrounding that's being cooled and heated. So you would get a less, I guess, you would get less effect to a certain extent as far as your cooling goes. It bring your performance down.